Well, thank you all for coming. It's really an honor to be able to stand in front of such a technical audience and talk to you all about mesh and the mesh services. At this PDC, I'm sure you've been hearing a ton about the mesh, and you've been noticing the ways in which it's starting to spread and kind of become integrated into lots of different applications and services across Microsoft. And you'll start to see it spreading outside Microsoft as well, and seeing its capabilities starting to light up other solutions as well. So there's a reason why you see this happening. And the simple reason is that the mesh is sort of an idea whose timing is just right. Now, I've been working at Microsoft for the past 13 or 14 years, and I spent 10 of those years working on Windows. So I've worked on every version from NT 4.0 through Windows Server 2008. And I can tell you that the mesh is at least as interesting and advanced as anything that's happened on Windows in that entire period. Well, why is it such an interesting advance? Well, what's happened over the past several years is that a change has crept up on us where we start seeing users interacting with more and more computing devices on an ongoing basis, whether it's PCs or mobile devices. And we've seen a need that's often unexpressed for software experiences and computing experiences that kind of step above the level of an individual device and that work across these contexts that users are in. There's a bunch of facilities that you need in order to be able to build experiences that work that way. And we've lacked them in Windows for a long time, and it's limited what we've been able to do in the platform up until now. So the mesh is simply filling in the gap, allowing us to take the platform to the next level. My name is Abaladig Badigashi, and I'm architect for the Mesh Cloud Services. Over the next hour, what I'll be doing is talking about how the mesh really works at its foundation, and how its cloud works, how its cloud scales, and how its cloud supports both the experiences that you see in the user interface on the web and on the desktop, as well as how it powers the live framework that I'm sure many of you have heard about, have seen in the hands-on sessions, and that you perhaps have lots of questions about. Towards the end, I'll also talk a little bit about the direction for the mesh services and the ways in which we'll be both extending the reach of the mesh into other experiences and services at Microsoft, into services outside Microsoft, and give you some insights for those of you who have built your own services that your software works with, give you some insights into how to think about leveraging the capabilities of the mesh services in your experiences to sort of achieve a better together picture and do some new things that go beyond what we've anticipated. By now, this picture is probably familiar. So you see on the lower edge the live services, kind of the building blocks on which a bunch of different things sit, including the mesh services. The mesh services are, broadly speaking, responsible for users, devices, and applications and synchronization. That's a pretty high level. This session is actually going to get into the details of what that means concretely. So a rough look at the flow that we're going to be walking through. I'll take a really quick look at the user experiences, just enough to motivate the architectural discussion that's going to follow. From the architectural discussion, we'll talk a little bit about the planning that went into building and designing the mesh, some of the strategies that we took towards building such a thing with the needs, with the scalability and availability needs that it has, and then actually how it's implemented, so like the technology that we applied and how it all fits together. I'll talk a little bit about what we've learned since the mesh has been up and running since earlier this year when we launched at the Web 2.0 conference, and some of the experiences and how that's led us to think about building services in general and about integrating with other services. And then I'll give you a preview of some of the things that will be happening in the future with the mesh. So out of curiosity, just by show of hands, how many people here have mesh accounts? Okay, that's pretty cool. So most of you have seen this UX. I'm not going to spend a ton of time on this. So you see here the live desktop. I'm signed in as myself, and I have 2 devices in the mesh for this particular user account. You can see up here, if I click on the live desktop, it effectively goes to a view of my mesh that's centered around the data that I've brought into my mesh, in this case, the mesh folders. Now, rather than spending a ton of time here, I'm going to make a really quick switch to another machine. Now, this machine is actually running inside a VM, inside a Hyper-V server. That Hyper-V server has two guest machines inside it. This Vista image, and then Windows Server 2008 image that's running a domain controller. Now, this probably looks just like the other picture that I showed you, but if you zoom in and you take a closer look up here, and apologies, we're going over a VPN connection to my office in Redmond, so it's not quite as responsive as you'd like, but the user account that's signed in here is not Hotmail or Live.com or any of the other accounts that you'd expect for Live ID. So what's going on? Well, what's going on is that you're actually looking at an early prototype of a mesh client that's integrated with the Microsoft Services Connector. So if you saw the Services Connector demo inside the keynote, then you know that basically what it does is you install it next to an Active Directory domain, and it connects that Active Directory domain with Live ID through the Microsoft Federation Gateway, and it allows you to sign in using the Active Directory credentials to any site that integrates with Live ID for authentication. So that's what you're looking at here. This is essentially a prototype of the mesh that allows me to sign in using domain credentials for a domain that I control, and that gives me all of the user experience, that I'm accustomed to in the mesh. We're going to come back to this later on, but for now, since most of you are so familiar with the mesh, rather than showing you the data experiences around the mesh folders and how you bring content into your mesh, I'll just give you a really quick demo of the client side of the prototype that I just described. So I'm going to sign in on this client with the same ID that you saw in the live desktop. And you'll see it'll start the sign-in process, and once the sign-in process is complete, it shows me a screen where I can add this device to my mesh. So what I'm doing here is I'm taking a machine, I'm using a credential that's part of an Active Directory domain to claim a device that's not joined to a domain so that I can connect it to a mesh that understands multiple contexts. So this is some of what we're going to be looking at in more depth later on. So I can add this device to my mesh, and then if I go back to the user experience, it'll show up on the live desktop. All right, so switching back to the slides. What did we actually see at work in these slides? So I added a new device to my mesh. Right? I was signed in as a user. So the first big primary service that the mesh provides is the account service, which you can think of as a focal point for keeping track of users, devices, applications, and relationships between them. All of this data becomes available for the experiences that are built on top of the mesh, whether it's the web desktop or the client user experience that you saw, and so on and so forth. The second major service that the mesh provides is it provides a replicated storage facility that's oriented around feeds as a way of getting a really broad reach. So we took a couple of bets inside the mesh. One of them was to standardize on HTTP as our transport. The other was to use feeds to represent all of the information that's in the mesh. I'll talk about some of the benefits that come from making those decisions later on. In addition to the feeds, the user data storage service also has the ability to store the content that's associated with those feeds. So if you imagine having a blog posting, you have a feed with a bunch of attachments in it. Well, this user data storage service can store both the metadata, which is the blob itself, as well as the content, which are the attachments. On top of that basic model, we've built the ability to synchronize those feeds across endpoints. And we've also built the ability to replicate the content that's associated with those feeds across all of the participants inside a mesh. So how does the content replication work? Well, it makes use of our communications and presence capabilities. Broadly speaking, there are two parts of this. There's the ability to know when devices are online. And that, for those of you who have used the mesh, when you use our remote desktop capabilities, the live remote, that's what you're taking advantage of. Now, the actual live remote connection makes use of a peer connectivity fabric that is designed to always be available and to always work, so that when it's possible to connect directly, it connects directly. When it's not possible, it falls back on a relay. That peer connectivity fabric is therefore shared both by the remote desktop as well as by the content replication. So we'll talk about some of the thinking that went into the design for that as well. So now the last major capability that you saw at work was our notifications capability. So we have a universe of devices. They're all interested in various pieces of information. You also have browsers that are interested in various pieces of information. So for instance, in the web desktop, you saw a device ring that showed you all of the devices that I had brought into my mesh. Well, that view needs to be able to refresh when I add a new device into my mesh. And so that means we need an asynchronous push channel to be able to efficiently get notifications of changes to all of the pieces of code that care about resources in the mesh. So that's the functionality that the notification service provides. In addition, the notification service is also what we use for bootstrapping peer-to-peer connectivity between devices, either because they want to replicate content or because they want to establish a remote desktop session. So let's take a step slightly higher and look at what are the concepts that are underlying the mesh. So I talked about being a user and signing in. Well, one of the top level resources inside every mesh is an identity. Now, the mesh is integrated pretty deeply with Live ID. What that means is that we rely on Live ID for all of our authentication. Now, in Live ID has always had support for authenticating users. And so when you're provisioned in the mesh, you get an identity resource that represents your sign up inside the mesh. Now in 4.5, IDS 4.5, the Live ID team added support for also authenticating devices. So now the way that support works is that when I downloaded the mesh client and I stepped through the wizard there, what happened is that behind the scenes, a public-private key pair was generated, and it was sent up to the Live ID cloud, which signed the public-private key pair, giving us a certificate. That certificate becomes the identity of the device inside the mesh, and it follows it around and is used for authenticating and identifying the device in various contexts. The last thing that happened is that actually made the device part of my mesh so that it would show up in the device ring. And that gesture we refer to as claiming the device. So I establish a relationship between an identity, the identity resource, and the device resource, so that we can use that to authorize things that the device tries to do on my behalf. So I've talked a little bit about HTTP and how we make use of feeds. Now, we made some fairly deep bets about how we were going to expose the object model that underlies the mesh in order to be able to power a flexible set of experiences, not just the ones that you see us shipping today, but the ones that you might be building on top of the live framework. But also to make sure that you could program against the mesh in multiple contexts, whether it's from the browser or from a rich client or from another cloud that's talking directly to the mesh services. So what does that mean concretely? Well, everything in the mesh is a resource. And what's a resource? Well, a resource is a resource in the HTTP sense, meaning that it has a URI that identifies it, and then it has potentially other metadata. One of the key pieces of information that we maintain for all resources in the mesh is a last update time, so you can tell when the resource has changed. Each resource lives inside a collection. A collection also has a URI. And then a collection, you can kind of think of it as being a scope for grouping resources together. So inside my mesh, I have a collection that represents the devices I've claimed. Inside each mesh folder, I have a collection that represents all of the files that are in that mesh folder, and so on and so forth. A collection is where you go to find out what has changed. So it has basic support for tracking changes, and it also has support for handling subscriptions. So if you want to get notified of changes when a collection, when something is added or removed to a collection, you can actually subscribe by visiting the subscription URI for that collection. So now both collections and resources are part of the object model. The way that we represent them over the wire is using feeds and items, either ATOM feeds or RSS feeds. We actually also have support for representing these as JSON or plain old XML. And then finally, how do you navigate between resources? So I have, a device claim. The device claim links both to my device as well as to me as the resource that represents me. Well, we use links to represent those. And links you can think of as just ways to navigate from one resource to another. And there's some information packaged inside links that tells us, like what the authorization is required to go fetch this resource from this other resource. So that's the background behind how the resource object model fits together and what some of the basic capabilities are. So now looking at the account service, so the provision state service that tracks users, devices, and applications, it integrates with Live ID at the top level for all authentication. Then it exposes HTTP to every application that's talking to it, whether it's the Live Mesh client on the desktop or it's the web desktop running inside a browser. The account service you can think of as effectively just a scale-out store for these top-level principles, users, devices, and apps, and the relationships between them. The Live Mesh client basically has a tiny cache inside it that caches resources from the account service so that when you're offline, you can still get things done. One of the benefits that we got here from standardizing on HTTP and REST is that we can expose the exact same APIs from the client as we do from the cloud so that you can build applications that can be pointed at the cloud and they'll work, or they can be pointed at the client and they'll work. So you can start to think about what this means, for building an application, that you want to have available in a browser, in a mobile phone, on the desktop and so forth. So this starts to open up possibilities and give us the reach that we want to be able to span all of the various contexts in which users compute. So enough about the account service. I skipped, because so many of you are familiar with the mesh folders experience. Because so many of you are familiar with the mesh folders experience, I skipped over the demo where I basically would have created a mesh folder and dropped some content into it. And then the mesh folder would have replicated to all of the devices in my mesh. So how does that actually work? Well, I said that we standardized on feeds as a way of representing information. In the case where the information corresponds to a file system folder that you've brought into your mesh, what we do is we have a feed that represents the folder, and then we have items that represent the files inside the folder. And the feeds that we store in the mesh are extensible, so you can attach extra information to them. In the case of replicating folders, the information that we attach includes, attributes, and the file name and so on and so forth. Enough information for you to be able to pick up this feed and materialize a view of the original file system folder on some other machine. The way that we connect the feed that's stored inside the cloud with the file system folder is using a thing we call a data feed mapping, which basically just binds the two together. So when you actually say that you want to have a particular mesh folder available on a device, what you're doing behind the scenes is you're establishing a mapping that says that feed should be available on that device. That allows me to actually simply replicate contents. But the mesh is about more than just replication. It's also about sharing. So being able to take a feed that you're replicating and share it with someone else. So in order to do that, you need to define what the scope is. In other words, who should be able to get a copy of this feed and go materialize it on their devices. The way that we do that is using permissions that are inside a scope we call the mesh object. So the mesh object is basically a wrapper for the data feeds that the mesh replicates that adds support for permissions and a few other basic capabilities. So using that as a background, it's useful to kind of just step back and say, I kept talking about replicating feeds. How does feed replication actually work? Well, one of the bets that we took is that we should standardize on a replication mechanism that doesn't work using a protocol, where you have to run the exact same code everywhere, but that expresses the information you're trying to replicate as data. So now the FeedSync specification, which was originally called the Simple Sharing Extension specification, does exactly that. What it does is it starts out with Atom or RSS, which are standard syntaxes for feeds. And then it defines a new element, which we call a sync element, that you can attach to each of the items inside a feed. And that contains a version vector and optionally a set of conflicts for the item in that feed. So now, that's the first thing that FeedSync defines. The second thing that it defines is a set of semantics for taking two sync elements that correspond to the same item, to the same feed item, and merging them in such a way that you end up with a single item. So now, if you take these two things together, the syntax and the semantics, you have everything that you need in order to enable bidirectional replication. And so that's exactly what we've done in the mesh. We've started out with FeedSync, and we've effectively built a huge scale-out FeedSync store, which is what the user data storage service is. So without knowing a ton about what it is that we're replicating, we're actually able to do scale-out replication for a variety of applications using an extensible data interchange format that supports everything from our file scenarios, folder replication, as well as contacts, discussions, and so forth. So now, just as the account service kind of has a little version of itself on the client, the user data storage service has a little version of itself on the client, which is a local replica as far as the cloud is concerned, with respect that keeps track of not all the feeds in the world, but just the feeds that this particular device cares about, either because a user who's using the device has mapped the feed to this device, or because an application, for instance, an application that's using the live framework, has said that feed needs to be available on the device. So now the way that the mesh folders application works, just to come back to it again, is that it starts out looking at a file system folder and it generates a feed representation of that folder, which it then pushes into the user data storage service on the mesh. And then the user data storage service on the mesh pushes that into the cloud, making it available for any other device to show up and pick up a copy of the feed and replicate it and reproduce the original file system hierarchy on that device. So now this pattern is useful to understand because it gives you an insight into how you would actually build applications of your own that integrate with the mesh, that pull stores that we potentially aren't aware of into the mesh. I'll talk a lot more about that later on, and in particular about how the sync framework makes it possible to bring data into the mesh using these mechanisms. So here's a look at what the overall architecture for the mesh looks like. So we've already talked about a couple of the top-level services, accounts and user data storage. I talked really briefly about notifications and communications and presence. One of the key things to take away from this slide is that the live framework is effectively a microcosm of the cloud in so many respects. So like if you're an architect, this kind of symmetry would just make you happy. Now, it has a tiny notification service inside it, so that applications running on the device can get notifications routed between one another even when you're offline. And it has a tiny communications and presence service inside it that allows you to bootstrap peer connectivity with other devices. On the cloud side, we integrate with Live ID and with the Messenger Relay service. The Relay service gives us kind of a fallback in cases where devices can't connect to each other directly. This gives us a fallback so that we can relay the content. And then on the case of on the client, we integrate with the Live ID client runtime library. So the only change that I made in the demo I showed where I signed in with an Active Directory credential is I just dropped a different version of the Live ID client runtime library with no changes to the mesh client itself whatsoever. Now, the LiveFX client also integrates with the Messenger NAT traversal, so that's how we get through NATs and firewalls. So here's roughly speaking what the overall picture looks like now. Along the center dimension, you see the components of the mesh that are built on top of the services. So we've already looked at the mesh web desktop which you saw inside the demo. We didn't look at mesh remote desktop, and we talked a lot about mesh folders. Now, what the live framework does is it allows you to add applications along this dimension that can talk in either direction, to either the client or the cloud. So now, we now have a way to have a universe of applications that spans these contexts. The question is, how do we make the whole thing scale? So now the mesh services have to support experiences that span, the mesh folders, remote desktop, stuff that we haven't anticipated yet that you guys folks are going to be building. The rest of this talk is going to talk about how we approach the problem. So how do we approach the problem? Well, the first thing we did is that we looked through the experiences that we were starting out with. So the mesh folders experience, for instance, where we're moving files around, the remote desktop experience where we're ferrying bytes back and forth, RDP messages that represent, what you see on your screen. And the challenge, and what we do is we derive the actual workloads that are going to be generated by those application flows. That leaves us a way to figure out what the scalability factors are going to be, whether it's going to be in terms of number of devices, applications, and so forth. And then we use that to figure out how we're going to partition state across our cloud and assign roles to the machines that we actually deploy inside our data centers. Here's a really concrete look at 3 flows that we worked through to decide how to build out the mesh. So the first flow that we'll look at is the startup flow. So a live FX client just boots up, it just came online. The second flow we'll look at is what happens when you drag a new file into a mesh folder, or when the mesh folder pulls a new file down from the cloud. And then the last flow we'll look at is how the content replication actually works across the mesh. So in the first flow, the first thing that a device has to do is it has a local cache, so it has to go figure out what's new. So in order to figure out what's new, it's just going to make a bunch of HTTP requests to our cloud. And then it's going to subscribe for notifications so that if anything changes after that point, it can find out about it. The next thing that it's going to do is that all of the content that it's replicating, so the feeds that it's replicating, it has to go update those. And it'll do that by making feed sync requests to the user data storage service in the next line there, and then subscribing for notifications again so that if any new files show up, it can find out about those. So now, when we think about this flow, how many devices typically are coming online at any given time? Well, the numbers aren't that high. So potentially this might be an okay scalability dimension. But we have to be careful because if you think about flash crowd scenarios, for instance, Patch Tuesday, you have a ton of devices showing up all at the same time because they've just been rebooted to install patches. And so we have to make sure that the cloud is designed so that it can handle those kinds of crowds. Okay, the file change scenario is actually quite a bit more interesting, and that's split into 3 phases. So the first phase is where the mesh folders application notices that a new file has been dropped into a mesh folder. So what it's going to do is it's going to generate the new view of the feed that has all of the file metadata, and it's going to push up the new feed up and onto the cloud. And in addition, it also has to pick up the bytes for the file itself and upload them to the cloud in the case where all of the content is being replicated to the cloud. So now think about how often does this happen? Well, this actually happens quite a bit more often because when you change a file on your file system, if that file is part of a mesh folder that's in your mesh, now we have to actually go through the feed sync logic each time. So this clearly is going to be a scalability dimension that we have to look at closely. So now, once you've actually gotten the metadata updated in the cloud, remember we have multiple devices that are participating in replicating this content. And so now they're all subscribed for changes. They're trying to find out when something changes in the folder so that they can pull the changes down. So now the cloud is responsible for firing off change notifications to all of those devices, which means that we have an additional multiplier on top of the load that we saw in the previous slide, which is the number of devices that are participating in replicating a particular mesh folder. We have to scale to accommodate firing off chain notifications. So now you can so now we have to decide whether we're going to do fan out, when the change occurs, or whether we're going to do fan out when a device shows up, to actually ask what changed and so forth. Once a device has found out that something changed in a folder that it's replicating, the next thing that it's going to do is it's going to come to the cloud and say, give me the new updated view of the feed that reflects the change you just told me occurred. So that's the beginning of the content replication scenario. So once it's gotten the metadata updated, now it has to go off and pull down the content that's associated with that change. So if you can imagine all of the devices that we just sent change notifications to, all showing up to our cloud and trying to pull down the exact same bytes, that's clearly not going to scale. So let's just not do that. So I jumped up ahead a little bit and I just assumed in this flow that we're going to use peer replication to solve this problem. So the next step in this flow is that a device figures out which other devices it can get the content from, and then it goes to the mesh communications and presence service to figure out, of the devices I could get this from, which ones are online right now. And then it goes off and establishes sessions to those devices, and they move the content around directly amongst one another. So now this can make use of a relay connection or a direct connection depending on the exact topology between the devices. All right, so let's see. So we've learned a bunch of things as part of walking through this flow. One of them is that the number of users is an important dimension for how we scale out the cloud, but it's actually somewhat less important than the number of devices. So both of those have to factor in our scaling out and our building out of capacity across the cloud, and across data centers. An additional point is that if you think about the scenario of a device that's a set of devices that are replicating the same content, that content is inside a mesh object. And in order to actually be able to scale, you want to partition on the mesh object itself so that if you have an extremely busy mesh object, you can push that to a particular cluster where you have the capacity, as opposed to having to partition it the exact same way you partition users. So you'll see exactly what that means for building out the cloud in one of the next couple of slides. Now, I talked a lot about firing off change notifications and how much load that would involve, depending on how we try to implement it. So one of the other things that we did to make sure that the cloud would scale and support not just our scenarios, but the live framework scenarios, is that we made a bet on using soft state to back a lot of the resources that we store in the cloud. So now because we're using commodity hardware, we have a limited number of IOs that we can afford to pay for any particular transaction. So anything that we can do using just memory without having to hit the disk is a net win for us. So we use soft state, for instance, to keep track of when devices are online. We use it to keep track of who has subscribed for change notifications, and we use it to keep track of the notifications themselves when we've sent them off until the time when a device comes online to pick them up. So far, the combination of soft state and partitioning gets us so far as making sure the cloud will scale in these multiple device scenarios. Another thing that we did that's kind of a deeper capability is that because we're built on top of HTTP and we took a bet on HTTP as our transport, we get the benefit of a lot of the facilities defined in HTTP. So there's native support for caching, which we just make use of directly with almost no new semantics. There's native support for tracking changes. So HTTP defines a process where you can hit a resource, and it has cache control directives that you can use to find out when the resource has changed. We just use those directly as they're specified in the RFC. And then the last piece is that if you imagine a folder that has, say, 100,000 files inside it, and you get a notification that the folder has changed, you do not want to go and enumerate all 100,000 to figure out what has changed. And so we have support for incremental state transfer. So when you hit the resource, you can say, I'm up to date as far as this version. Just tell me what's new. And that's consistently supported across all the resources that we have in our cloud, whether it's data feeds or whether it's your feed of devices that you brought into your mesh and so forth. So because we had that as a foundation, we are actually able to go even further. And instead of some resources, we actually don't even store the master copy in the cloud. We store it on the client. And we have mechanisms, a protocol whereby we can get the master copy from the client if we have to recycle the server in the cloud that's currently responsible for holding on to it. And then the last piece of our scale-out strategy to make sure the cloud scales is we use peer connectivity for moving content around. Okay, so I talked a bunch about partitioning. So what does that actually mean concretely? So we have a bunch of resources, users, devices, the folders that you're replicating inside mesh objects. Now we have multiple locations where we have machines. We have data centers, across the world. So how do we make sure that we've split all of the resources that we have in such a way that it takes advantage of the capacity that we have? Well, our starting point is that each resource is assigned a home data center. That's where it lives. Now, every resource has a stable identifier. Remember, the resources are all HTTP resources, so they have URIs. And the stable identifier has the resources IDs encoded inside it. So there's a domain name, which is accounts.mesh.com in this picture, and then there's a couple of opaque pieces of information, which you may have seen if you've gone through our hands-on labs and you've looked through the data model browser. So now, in order to figure out from a resource URI where the resource lives, all we have to do is we have to do a lookup inside a replicated database using these two pieces of information as the lookup keys. So now a client shows up, it does a DNS lookup, that tells it where one of our data centers. It hits one of our data centers. If it's the wrong one, the data center can just look at the URI that the client is fetching, and that gives it enough information to figure out, okay, where should the client actually go? So now, in the case where the client actually hits the wrong data center, we just use an HTTP redirect to send it to the right place. So that results in a URI that looks a little bit like this. So it has an additional piece of information encoded in it, which is the fixed data center. And again, because we're using HTTP, which has native caching support built in the case where the client hits the wrong place, we send a redirect, and then the client can cache that redirect so the next time the client doesn't just hit the wrong place all over again. Okay, so it's a general service design principles. We use commodity hardware wherever we can. We've talked already about partitioning and how we use that to scale out to make sure that we can just add capacity by adding data centers. We'll talk a bit more about loose coupling and how that enables us to work seamlessly across all the roles that we have in our cloud. The model for actually deploying bits from our servers to the clouds that are running in the data center is an extremely simple model. It's just the same Xcopy deployment and configuration model that you'll be able to take advantage of in the Azure Services Framework. And then finally, when it comes to dealing with errors that happen in the cloud, we have an extremely simple model, which is fail fast and then just recover from there. So the loose coupling is important for making sure that the fail-fast recovery model works and that the cloud scales, and it's extremely cheap, not just to build out, but to operate. All right, so let's take a look at the actual infrastructure that the mesh runs on today. So we have a standard SKU that the services fabric that were built on top of mandates, which is great for us because it simplifies our life in terms of thinking about what the workloads are that we need to support and what resources we have on each machine. So we know how much memory we have, we know how many IOs we have per second on the disk, and we know how much network bandwidth we have. The services fabric takes care of most of the general service design principles that I talked about. So it's commodity hardware. You just add machines and it discovers that the machines are there and picks up and assigns them roles. It's an Xcopy deployment model, and it automatically rolls back to the previous version of a service application, if the rollout detects that there's a problem. And then it allows the service to monitor itself, and when the service reports there's any problem, it has recovery actions, starting out with, simply restart to, reboot the machine, to re-image the machine, and if that doesn't work, just take the machine out of rotation. So the actual roles that we run in the data center, meaning the actual machines that run inside the data center, are broken up this way. There are front-end roles which actually field HTTP requests coming from either browsers or clients off of the network. I'll talk about what's inside each one of those these front-end roles on the next slide. There's back-end roles, which are a combination of the scalable storage, so all of the state that actually has to be written out on disk just makes use of the scalable storage capabilities of our services framework. And then there's a bunch of soft state roles where we just store the state in memory, and I'll talk about how those roles work as well. And then we have some infrastructure roles that are responsible for things like keeping track of the health of the service, keeping track of who's responsible for what, and so forth. So now, if you take all of these together, this constitutes a scale unit for our cloud. So this is a set of machines that we think about and we deploy as a unit. If we need to add capacity, we have a certain number of account API machines, a certain number of user data storage machines, and so forth. And we just build those out and add capacity that way. So we know when we add a new scale unit that it will give us this many, support for this many new users, this many new devices, this many new mesh objects and feeds. And you can see along the center column that the partitioning units define the makeup of individual scale units, a combination of the partitioning unit and then the workloads that we have to support, which we walked through earlier. All right, so this is the view of the mesh cloud from an infrastructure level. From the perspective of how it's actually laid out, it looks something like this. So you have the services fabric again, which is the foundation for the entire cloud. Underneath that, you have Live ID, which we rely on heavily for all of our authentication. The messenger relay service, which we rely on for all of our communications, content replication, remote desktop, and so forth. And then Hotmail, which I'll talk about in just a moment. On top of the services fabric, the front-end roles are the web desktop, which you see when I sign in, when I signed into the web desktop, and I showed you a view of my device ring. There's a composite role which includes multiple actual services. So in looking through the workloads that need to be supported by the accounts service, the front ends, the communications and presence services, and the notification service, we noticed that the resources that they're making use of are actually, they're not really in conflict with one another, so we can actually just run them on the same machines. And so this is a composite role that actually has multiple service applications running inside it in our data center. This user data storage API is a unique role. It has to handle the feed sync merge operation. It also has to handle some of the peer connectivity bootstrapping logic. And so we run that on its own machine. And then finally, we have the content upload and download, which is primarily doing streaming back and forth in and out of our data center for the content that users have decided to bring into their meshes. So that is also its own role. So the back-end roles inside the mesh are split into two categories. There's the soft state roles. So I mentioned that we use memory wherever we can to store state to avoid having to pay IOs for answering incoming requests from clients. So the soft state roles are used for keeping track of device presence, which devices are online right now, as well as keeping track of notifications that a service has generated for a client, but that the client hasn't yet dequeued. A common back-end service that's used across the cloud is a subscription store. So I mentioned that in our object model, all resources live in collections, and collections support subscriptions. When you go to subscribe to a resource, the subscription you posted goes into a subscription store, and we actually store that just in memory. We don't want to write that out on disk because it's such a piece of transient information. To make that possible, we just have a time to live associated with it so that it times out, and the client is responsible for republishing it if the client is still interested in that subscription. And then finally, we actually reuse some of the logic for the subscription store and the other soft state stores to allow our web desktop to have a scale-out dictionary store that it can use to keep track of web session information, so UI elements, positions of windows on the screen and so forth. So the second category of back-end roles that we have are the reliable state stores. So all of these, what these all have in common is that they actually have to write data out to the disk. So now, the way that we do that is we just use our scalable storage infrastructure. That's part of the Azure Services framework, and that you all will be able to make use of once you have your CTP tokens. And so the three categories of state that we store persistently are accounts information, users, devices, applications, relationships, and then the user data, so the replicated state themselves, the feeds that are being replicated, and finally the content that has been brought into the mesh by users. The glue that keeps this all running and that keeps the system healthy is, first of all, the watchdogs, which integrate with the services fabric and which are constantly monitoring all of the services to make sure that they're healthy and reporting the status of the services that are down so that the services fabric can take recovery actions. And then in the center there, the partitioning and recovery manager, which is kind of the which is the engine that we that we use to enable soft state, which I'll talk about on the next slide. So the partitioning recovery manager, you can think of it as basically just a distributed lease manager. So we have a bunch of nodes in our back end that are ready to hold on to state in memory. And we have a bunch of resources that we have to assign to nodes. And so the partitioning and recovery manager basically assigns responsibility for resources to nodes. The way it works concretely is that we have an owner library, which runs inside a backend that keeps track of that's responsible for holding on to soft state. And then we have a lookup library that lives inside a front end or any other node that needs to interact with soft state to find out where it lives. And then the partitioning and recovery manager just hands out leases and makes sure that at any given time, at most one node believes that it's responsible for keeping track of any piece of state, whether it's a device presence record or whether it's a notification queue. Internally, the way that the partitioning and recovery manager works is it uses consistent hashing to assign responsibility for all of these resources across the nodes. And then it also has capability for tracking the availability of nodes so that when a node goes down, it can fire off a notification so that if a client really cared about the piece of state that was just lost, for instance, a subscription to notification for changes, the client gets notified and it can show up to our cloud again and repost the exact same state. So here's a look at the software stack that's common between the front ends and the back ends that we run. So the basic infrastructure is all running on top of Windows Server. The Services Fabric controller actually owns the machine in a sense. And then our logic runs as a service application on top of the Services Fabric controller in Windows Server. Each service process consists of the services runtime, which has some basic common capabilities that they all make use of. And a service application or multiple service applications that implement things like device presence, feed sync support, and so on. On the right-hand side, you see the tracing and log collection, which is part of our monitoring logic and keeps track of when machines are up and down. So now the way that the stack gets instantiated in the case of a front end is slightly different from the way that it gets instantiated in the case of a back end. In the case of a front end, we're basically handling HTTP requests coming from clients, right? So the starting point is that we have a set of handlers, which will look very familiar for accounts, notifications, communications and presence, and user data storage. So all of these are resources, and we just have handlers that listen for incoming requests, and underneath them is the routing logic that is used to send requests to the right places. In the case of the content front end that handles streaming of uploads and downloads, what that does is it's basically sitting inside a similar framework that's optimized for handling content as opposed to optimized for handling CRUD operations against HTTP resources. Underneath both of them is a request dispatcher that looks at the incoming URI and figures out which handler should handle it based on that. It's an extremely simple model. The request dispatcher makes use of WCF and its syndication support for handling the routing requests, and all of this sits on top of HTTP.sys. So we're basically using off-the-shelf components in this context to enable this scale-out capability in all of our front ends. Now, one of the features that we'll be bringing online in the next few months is the ability to stream notifications not over an HTTP push channel, but over a TCP push channel. So in the case where you have a client that actually has the ability to connect out directly as opposed to connecting using HTTP, this is a big win because you can stream notifications directly as opposed to using an RPC over HTTP style notification pattern where the client has to post a request, and when the client posts a request, then you can complete the response with the change that happened. That notification streaming sits on top of a stream dispatcher that's very similar to the HTTP dispatcher, and that just makes use of the built-in sockets capabilities. Some of the runtime capabilities is the soft state lookup that I mentioned. So the front ends that are handling requests for things that are stored in soft state stores need to be able to look up that soft state. And we have a client that understands how to talk to our scalable storage for the resources that are actually stored persistently. And then the subscription support is similar. It's just a library that the front ends can make use of to manage subscriptions. Now, in the back end, the software stack looks quite different. So first of all, for our persistent storage, we don't actually really need a back end because we just use the scalable storage. So primarily, this role is concerned with the soft state stores, so the things that we store in memory. That includes device presence, notification queues, dictionaries, and so forth. And those sit on top of a sockets dispatcher, very similar to the one that we use for streaming TCP notifications. It sits on top of sockets, and the services runtime capabilities are more or less the same. So now I'll switch over and take a really quick look at what it's like to monitor the cloud that you just saw. So what you see here is a really quick look at one of the operational consoles that we keep track of to figure out the health of the cloud. So you see on the left-hand side a view of the device identities and devices that we're currently storing. If you look on the lower right-hand corner, you see our availability inside Keynote. So we use Keynote to monitor the availability of the site from the perspective of users, and we feed that data into our console so we have an aggregate view of it. In addition, up here, you can actually see the current storage that's in use, and you can see actually over time how adoption of the mesh, we've increased the amount that we're storing at a pretty rapid pace, and we've been able to just add capacity, to handle that, based on the design that I walked through earlier. Another view that we have inside the operational console is just keeping track of the health of the boxes themselves. So this is a quick look at the CPU utilization for some of our front-end boxes over time. In general, we want to keep it at roughly this level. You'll see spikes under certain circumstances, and whenever we see those spikes, we always take a look to understand better what's going on under the covers. There are a few other things that are useful to point out about this particular view here. Now, on the left-hand side, you'll notice that there are actually multiple clouds that we operate on an ongoing basis. So most of you have worked with the mesh.com site because that's where you went to sign up. But we actually have the ability to run many, many, many instances of this cloud. So when you sign up for the developer CTP, for instance, you're actually signing up for a slightly different cloud than the primary cloud that we operate, for general user availability. The last view that's that's interesting to look at is this one, which we're still working on, but which effectively will be showing a view across all of our user population, across the devices. What are the devices that are currently online, and what does the topology look like for the peer content replication? So this will give us a really cool way to understand where are the hotspots. Do we see lots of cross-continental traffic? Like, what are the patterns, inside the country, so that we understand in advance how we should build out capacity, where we need more bandwidth, where we're potentially underutilizing our bandwidth. All right. So we learned a bunch of lessons, as part of operating the cloud over the past few months. You can sort of read through these, and I'll tell you a couple of key things that we learned. So now, on availability, there are certain things that you just can't plan for with availability. Just earlier, not so long ago, you probably some of you might have had to deal with a patch that was released out of band, and that was kind of a critical patch. Well, we had to deal with that as well. And in fact, the fact that we had adopted this kind of recovery-oriented X-copy deployment model meant that we were able to patch all 1,100 of our servers in a matter of hours, because it was simply a matter of taking the machine out of rotation, applying the patch, and bringing it back into rotation. So that's the kind of thing that we had to design for in advance, and that we had to plan for to make sure that we could operate the cloud efficiently. On monitoring, it's important to gather as much information as possible, but it's also important to refine the information that we keep on an ongoing basis. Today we generate gigabytes of logs, on a daily basis that represent, all of the activity across the mesh. So what we've had to do is we've had to build infrastructure for picking up those logs and dropping them inside a data mining facility that we have, so that we can do queries against it, so that we can quickly diagnose issues and understand patterns without having to do massive amounts of text processing. On deployment, we're actually able to use the fact that we've ramped up gradually to learn quite a bit. So we started out small, and we were able to refine our deployment processes, as we issued releases. So we've sort of been on a roughly every other week we're deploying something to the cloud. In general, client upgrades are more involved, and so we roll those out every quarter or so right now. The key thing to point out here is that any time spent on understanding the upgrade path in advance pays off in spades. And so, for instance, we've learned to simulate the upgrades repeatedly using all of those extra clouds that I showed you, to make sure that any issues that are going to show up as we go from one version of the cloud to another, one database schema to another, we find out what those are early. So that's it for the mesh as it is today. The rest of this talk is going to look at some of the future stuff that we're working on. So how do we think about extending the mesh? So I already talked about extending the mesh from the perspective of authentication. So being able to authenticate new kinds of users, or being able to federate, with Active Directory domains. So that's an initial step, but there's actually quite more to this than I've shown you so far. One thing I haven't shown you today is being able to take the mesh and the user data storage service and point it at other clouds. So pointing it at, for instance, SmugMug, or Flickr, or Netflix, anything that exposes a feed, and being able to bring the contents of that other store into the mesh so that you can work with it in the experiences that you're building on top of the live framework. Now, some of you may have gone to the sessions on the sync framework. And you may have seen some of the work that they're doing to enable new sync providers, so that you can effectively just build a sync application that plugs in a provider from, say, SmugMug, or it plugs in a provider from Flickr, and it acquires the ability to synchronize content from that store into your application store. So I'll talk about what that means for the mesh in a couple of slides. The ultimate dimension of extensibility for the mesh is being able to take the entire cloud and make it available, for instance, in a personal context. So you can imagine, say, a Windows home server scenario where you actually have your own user data storage service that has your own content that you have control over. Similarly, in the enterprise, enterprises will want to have control over the confidentiality of the data that they have, while also getting the benefits of the mesh so that they can span the computing context. Their users can take data offline subject to enterprise policy, and so forth. Now, that actually splits into two dimensions. There's the on-premises hosted solution, where you just have your own storage service on your premises. And then there's the kind of co-located solution where Microsoft operates a user data storage service that's just for a particular enterprise. So we're starting to think about those dimensions of extensibility and applying some of the mesh technology in those scenarios as well. So you saw the services connector stuff scenario working today in a basic way in the prototype. Those of you who went to the sync framework session saw the early version of using the sync framework to sync from Flickr or from SmugMug or from PhotoBucket directly into the mesh. Stay tuned for more about the enterprise and personal storage services, and send us lots of feedback. As you use the live framework, think about the scenarios that you're building and give us feedback about what capabilities you'd like to see added. So a quick word about the identity federation scenario. I talked through this really quickly. We add a services connector instance into an on-premises Active Directory installation. That talks to the federation gateway in the cloud, and the federation gateway in the cloud allows the live mesh client and the live mesh cloud to communicate using Active Directory credentials. So that will be coming soon. Now, there's actually more to this scenario, because if you think about what an enterprise wants, not only do they want to be able to use their Active Directory credentials in multiple contexts. They also want to make sure that enterprise policy is enforced. So who can do what with their active credentials and where. So now, those of you who have gone to the sessions on Geneva have had a preview for the way that we're thinking about using claims-based authorization and authentication to solve some of these problems. So the feedback, my request to you would be, think of, as you use the live framework and as you use Geneva, think about how the mesh comes together with those capabilities to enable some pretty interesting scenarios and new applications that go significantly beyond what you've seen so far. So I talked about the sync framework quite a bit, and it's useful to actually go deeper and understand exactly what I was saying. Now, the live framework we already talked about, and we talked about how the live framework works against the Mesh Services Cloud to keep a user's data in sync. Now, what the sync framework does is that it allows you to build sync applications that pull in providers that various people will be making available as part of a new ecosystem that they're bootstrapping. So you'll have C providers for the live mesh itself, for online services like SmugMug and PhotoBucket, for our solutions like SharePoint and so forth. So the sync framework will kind of become a hub for exposing the capabilities of your store in a way that allows other people to work with the data inside that store. So now the sync framework today actually integrates with the live framework, meaning that the sync framework has the ability to generate a feed sync feed that represents any set of changes that you're trying to synchronize inside a synchronization session. Using that ability, they've actually been able to demonstrate using the sync framework to just push changes directly into the mesh. However, that requires you to be running a client application of your own. So typically, you're running, an agent on a desktop, and that agent goes off and talks to some external store, pulls the changes down, and then pushes it up into the mesh, which isn't necessarily what you want. What you might want instead is the ability to just tell the mesh, I would like to connect this particular feed with this other particular feed, and I'd like you to make use of the capabilities inside the sync framework to bring these feeds together and keep them in sync in a way that respects permissions, in a way that potentially leverages Active Directory credentials, in a way that uses claims-based policy to enforce business expectations around how data moves. So the cloud synchronization scenario is one that we're starting to think about now, and that we think has the potential to actually be fairly interesting by making the mesh services more than just a consumer solution, but by making them a synchronization hub for the services that you might be building and for the applications that you might be building. So with that, what we've covered, first, the mesh services are kind of unique in the live services platform in that they're a finished service, and so rather than just being platform technology, they span the gamut from the user experience all the way down to the very plumbing, and they do that at the same time as they're delivering capabilities that you can use in your applications to build out, to light up your apps in new ways. So you can build on them today. The two starting points for building on the mesh are the live framework and the sync framework. So for those of you who missed the sync framework sessions, they'll be online later on, and I'll have references to them on the next slide. And then finally, give us lots of feedback, because there are lots of dimensions in which we could extend the mesh. There are lots of directions we could go. Knowing which ones to pick first, will depend on what people tell us is important to do next. So whether it's supporting enterprise policy, whether it's supporting cloud synchronization, all of these are possibilities. So it's just a question of figuring out what's the most valuable and what do we do next. And so here are a few related sessions. The pointer to the landing page for Live Mesh and our blog, where there will be a post either today or later on this week, talking in some more depth about some of what I've covered. And we have a few more sessions here at PDC. For those of you who missed the Lap Around Live Framework and Mesh Services session, that's a good way to understand how the Live Framework connects to the Mesh Services I've talked about. Tomorrow, John McIntyre will be talking about the notifications and communications capabilities of the mesh in a lot more depth. The sync framework sessions are already passed, but you can go check those out online at the PDC website and check out their MSDN Developer Center. So please fill out your evaluations, and I'd be happy to take questions. If you could just walk up to the mics if you have any questions.
Do you have any kind of estimate as to looking at the landscape of the internet today and all of the devices that are out there and all the ways that the cloud could be leveraged? Do you have any idea what percentage of the time you'd be able to actually initiate point-to-point communications instead of going through a relay?
We think that if we build some of the capabilities that we're currently working on right now for our next release, we should be able to hit 85% and possibly slightly above 90% based on the data we have from Messenger.
Two questions. One, do you use Velocity by any chance to do the soft state replication?
Not yet. Not yet. So now the work on the mesh actually started about almost 3 years ago now. So Velocity actually just didn't exist.
Okay.
And so we're working really hard on sort of integrating, with some of the capabilities that they have.
And then the other thing is, do you support the HTTP range header for content upload and download?
Not yet, but it's on the list. Question over there?
Is folder share now built on top of mesh?
Not yet, but it's one of the next things on the list, integrating the folder share technology, which is more of a file sync specific solution, with the mesh technology, which is, as you can see, is quite a bit broader in terms of its reach.
Right. And also, does it cope with multiple users on a single device?
Oh yes, it does. So you can have multiple people claiming the device, and you can have, so it works fine.
And can they share a folder?
Yeah, with one another, yeah.
So it's a single folder, 2 users, 1 device?
Yeah, now there are some strange things that happen when you do that, but it basically works.
Cool, thank you.
Question over there?
No, sorry.
Oh, I see. Could you walk up to the mic just so people can hear? Yeah, right there.
Yeah, can you share a little bit about your experience of integrating SAML with REST for the claims base? Because
I see. So now, I mentioned that we're built on top of Live ID. So now the tokens that you get back from Live ID when a user signs in are actually SAML tokens. They have a compact token, and then they have a SAML token. So in our case, we're just sending that token in the authorization header. Now, in addition, some of the stuff that I didn't talk about, which is kind of a little more deep, is the way that we handle authorization in the mesh. So for instance, when is a device authorized to talk to another device? When is a user authorized to see a mesh object? The way that we pass that information around is also using SAML tokens. And so we just use the usual HTTP mechanisms defining a realm that corresponds to mesh, and you having the SAML token be the authorization header and the incoming request.
Are you doing any negotiation of claims, or is it just statically known what claims you need?
Well, let's talk offline. Just come up, because it's interesting what we do. It's self-discovering, so it's not statically defined, but it's designed so that a client can dynamically discover what claims it needs to go fetch in order to interact with the resource. Question right there?
Yeah, hi. Early in the presentation, you were talking about an asynchronous push to the client. Is that truly a push, or is it more metaphorically a push?
Well, today, with the HTTP notification channel, it's asynchronous. It's more or less like RPC over HTTP, meaning the client has to issue a GET request, and then we respond. With the TCP notification channel, which is up and running now and will be in the next release, it will truly be a push.
Great. And is there a roadmap to having mesh be on the Azure platform?
Say again?
On the Azure cloud, would this be moving to that frame? That
well,
infrastructure?
We're actually using Azure technologies today.
Okay. Great.
Okay.
Thanks.
Question right there.
Yeah. Can you disclose anything about the size of your user base or number of devices connected to the mesh at this stage?
We're not releasing a ton of information about that today, but if you let me know what you're looking for, we can just come up afterwards.
Okay.
I mean, the cloud is designed to scale to the live ID population, which is millions. Question right there?
I have the same question as one of the previous questions, which is, so you said you're running on top of Windows Azure now?
No, we're using some of the Azure technologies. So we're transitioning gradually as we build out the cloud.
Okay, so in the future it will run on top of Windows Azure. What about SDS? Will it run on top of that as well?
Well, right now, for our scalable storage, what we've done is we've designed it so it has an abstraction layer. We're trying to migrate as quickly as we can, but we're also growing at the same time. So a lot of these decisions are just a matter of timing, and how much change we can take on in any given release.
Okay, and I have another question about what you said about Xcopy to deploy. What I didn't understand is if the DLL, for example, is running at that moment, then I don't think you can copy over it.
Oh yeah, but the deployment model is Xcopy, meaning it's not, you don't have to go change a bunch of registry settings. The service application has to be designed so that it can just run as a bunch of files in a directory.
I see. So you actually have to stop the service, do the Xcopy, and then start the service. Okay, thank you.
Question right there.
I'm just curious, when will we see the client and SDK available for like Windows Server 2008?
Which SDK for Windows Server 2008?
For Live Mesh.
The Live Framework SDK is available today.
Okay.
Is that what you're referring to?
The client as well.
The Live Framework SDK allows you to talk directly to the client. So the client is available as a free download. You can just go to mesh.com.
It won't install on Server 2008 right now.
Oh, I see. There's a workaround for that. Just come over here, and I'll tell you what the workaround is.
Okay.
Sorry. Other questions? We'll post it on the blog. How's that? All right, thanks. Thanks, everyone.